Artificial light accounts for approximately 20% of the total electricity consumed globally. Considering the present environmental crisis, this makes the discovery of energy-efficient light-emitting materials particularly important, especially those that produce white light. Over the last decade, technological advances in solid-state lighting, the subfield of semiconductors research concerned with light-emitting compounds, has led to the widespread use of white LEDs. However, most of these LEDs are actually a blue LED chip coated with a yellow luminescent material. The emitted yellow light combined with the remaining blue light produces the white color. Therefore, a way to reduce the energy consumption of modern white LED lights is to find better blue-emitting semiconductors. Unfortunately, no known blue-emitting compounds were simultaneously highly efficient, easily processable, durable, eco-friendly, and made from abundant materials, until now. In a recent study, published in Advanced Materials, a team of scientists from Tokyo Institute of Technology, Japan, discovered a new alkali copper halide, Cs5-copper-2 chloride I2, that fills all the criteria. Unlike Cs3MULTIVALENTCU2I5, another promising blue-emitting candidate for future devices, the proposed compound has two different halides, chloride and iodide. Although mixed halide materials have been tried before, Cs5-copper-2 chloride I2 has unique properties that emerge specifically from the use of I- and C- ions. It turns out that Cs5-copper-2 chloride I2 forms a one-dimensional zigzag chain out of two different subunits, and the links in the chain are exclusively bridged by I- ions. The scientists also found another important feature: its valence band, which describes the energy levels of electrons in different positions of the material's crystalline structure, is almost flat, of constant energy. In turn, this characteristic makes photo-generated holes, positively charged pseudoparticles that represent the absence of a photoexcited electron, heavier. These holes tend to become immobilized due to their strong interaction with I- ions, and they easily bond with nearby free electrons T. Excitons induce distortions in the crystal structure. Much like the fact that one would have trouble moving atop a suspended large net that is considerably deformed by one's own weight, the excitons become trapped in place by their own effect. This is crucial for the highly efficient generation of blue light. Professor Jungwon Kim, who led the study, explains, the self-trapped excitons are localized forms of optically excited energy. The eventual recombination of their constituting electron-hole pair causes photoluminescence, the emission of blue light in this case. In addition to its efficiency, it is exclusively composed of abundant materials, making it relatively inexpensive. Moreover, it is much more stable in air than Cs3MULTIVALENTCU2I5 and other alkali copper halide compounds. The scientists found that the performance of Cs5-copper-2 chloride I2 did not degrade when stored in air for 3 months, while similar light-emitting compounds performed worse after merely days. Finally, Cs5-copper-2 chloride I2 does not require lead, a highly toxic element, making it eco-friendly overall. Excited about the results of the study, Professor Kim concludes, our findings provide a new perspective for the development of new alkali copper halide candidates and demonstrate that Cs5-copper-2 chloride I2 could be a promising blue-emitting material. The light shed by this team of scientists will hopefully Story source: materials provided by Tokyo Institute of Technology. Note: content may be edited for style and length. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.